What's going on, everyone? I hope everyone's well. Today for me it's a beautiful day, the sun is shining, it's a bright blue sky, and my neighbours that I share a wall with have finally finished preparing their 10-course breakfast. This means that I can start recording question 34, the Quanta to Quarks section of the 2017 HSC Physics paper. So, Part A, Part 1 asks, state the composition of the helium-3 nucleus in terms of fundamental particles. In this case, the helium-3 nucleus is missing something. So helium-3 is not the normal helium gas that inflates our helium balloons. That is helium-4. Helium-4 contains 2 protons and 2 neutrons. Helium, which has an atomic number of 2, always has 2 protons. In this case, helium-3 is missing something, and it's missing a neutron. That means it's containing 2 protons and 1 neutron. Each proton and neutron are also made of 3 quarks. So it's a 2-mark question. We just had to state the composition, and that's what we've done. That's our 2-mark question. Question 2 says, outline features of the strong nuclear force. 3 marks. The strong nuclear force it's a very strong and attractive force between nucleons. And a nucleon is either a proton or a neutron. So these are the things that make up our nuclei of whatever atoms that we're talking about. And it's the strong nuclear force that holds all these nucleons together. It's independent of charge and exists between 2 protons, a proton and a neutron, or just 2 neutrons. It's a very short range force of about 10 to the minus 15 meters, so that each nucleon only interacts with its nearest neighbors. So each nucleon only interacts with one nucleon, or one of the nucleon that's touching it, or very close to it. It can't interact with it. That's 2 or 3 nucleons away. This force also tapers off at about 2.5 times 10 to the minus 15 meters. And it's responsible for overcoming the Coulomb repulsion that tries to separate proton-proton pairs. So protons, at that distance, are pushing each other apart very, very strongly. But the strong nuclear force is so strong at this distance that it overcomes that repulsion and still holds them all together. If we were to graph it, we could look at it like this. So we'd have force between nucleons on our y-axis, and we'd have the separation of the nucleons on the x-axis. We'd also have a force of repulsion and attraction. Now, at very short distances, the strong nuclear force is actually repulsive and pushes nucleons apart so they don't get too close. But that's only below about 1 femtometer, which is 10 to the minus 15 meters. So if we want to draw what this looks like, how this force changes over distance, it would look like this. It's going to look approximately like this. So it tapers off at about 2 times 10 to the minus 15 meters, where that should actually be touching 0. Yep, that's pretty good. So we can see that it's repulsive below 1 femto, or below about half a femtometer, and it starts to become attractive above that half a femtometer, and really peaks around 1 femtometer. That's when it's at its strongest force, strongest attraction, before it zeroes off. Okay, so that was part 2. So question B, part 1, says, distinguish between the processes of nuclear fission and transmutation. 2 marks. So, transmutation is a naturally occurring process where one element decays into another, whereas nuclear fission is an energy-releasing process where uranium-235 is broken up by the bombardment of slowed neutrons. So, transmutation occurs via alpha, beta, or gamma decay. These are the most common types of radioactivity that we're exposed to. Alpha decay is when a helium nucleus is released. Beta decay is when an electron is released, and gamma decay is when gamma radiation is released. So this occurs when certain elements, radioactive elements, are decaying, they're giving off something, and they're slowly starting to turn into something else, depending on what they're releasing. That's for transmutation. And it doesn't release any energy in this process. Whereas uranium-235, when that undergoes nuclear fission, it produces huge amounts of energy, it produces more neutrons, releases more neutrons, which bombard other uranium-235 atoms, which break it up. So it's a physical, stimulated breaking up of the atom. It doesn't occur naturally. It only occurs really in the lab. And it only occurs with uranium-235, or also plutonium-239, but that's something else. Part 2. The diagram shows some components of a nuclear reactor. 2 marks. So we've got a diagram here, straight from the HSC paper. We've got fuel elements, we've got a moderator material, and we've got a control rod. We have to explain how labelled components work together to produce a controlled nuclear reaction. So first of all, I'll read my answer, and then I'll explain it in a bit more depth if I think that's necessary. So, the fuel rods are made of uranium-235 or plutonium-239, fissionable materials that release neutrons to stimulate the fission of other atoms. The moderator material slows the neutrons down to increase the number of neutrons captured. The control rods capture neutrons, controlling the reaction rate, making sure the reaction does not become uncontrolled. Cool. So, nuclear fission only occurs when you have A, enough uranium-235, or you have a critical mass of uranium or plutonium, and you have a way to slow those neutrons down. If the neutrons are moving at their full speed when they're released from from an atom that's breaking apart, then they'll be moving way too fast to be captured most of the time. So you have this moderator material which slows the neutrons down, and that allows them to be captured by other uranium-235 atoms, which are then broken up and then release more neutrons. Now, every uranium-235 atom that breaks up always releases 3 neutrons. And if all of these neutrons are allowed to bombard with other uranium-235 atoms, this produces an uncontrolled nuclear reaction. We don't want this to happen, so we actually absorb some of those neutrons using the control rods. Those control rods, like something like cadmium, which will absorb, about 1.2 or so of those on average of those neutrons that are released, and that means that there's a controllable amount of neutrons that are being absorbed by the uranium-235, and that produces a controlled reaction. It's not something that's going to get too hot, and it's not going to be a runaway reaction. But you don't need to include all that information. All you need to include is roughly what I've written there. We just need to explain how those labelled components work together. Keep in mind, it's only a 2-mark question. It doesn't need to be too detailed. Alright guys, I might end the video there, and I'll answer questions C, D and E in the next video. If you liked this video, please give it a thumbs up. If you disliked it, please let me know in the comments what I could do better and what you disliked about the video. And if there's anything else you'd like to see, please leave a comment below. Okay guys, have a great day.